the Honorable Professor Xuan Dong, Mr. Ivan Lee, Mr. Eddie Zhang, distinguished guests, some of you have traveled from afar, colleagues, ladies and gentlemen, good morning. It's my great pleasure and honor to welcome all of you to the opening ceremony of the 2024 Future Science Prize Week. This event is jointly hosted by the Future Science Prize and the Hong Kong Academy of Sciences. In my capacity as the co-chair of the 2024 Future Science Prize Week Program Committee, together with Professor Douglas Lin, we would like to extend our heartfelt gratitude for your presence here today. Today marks not only the 9th year since the inception of the Future Science Prize, but also the 2nd time we host the Future Science Prize Week in Hong Kong. Hong Kong has a number of world-class research universities, with 5 ranked amongst the top 100 universities in the world. We also have outstanding talents in science and a supportive and rapidly developing environment of innovation. Among the 39 laureates awarded the Future Science Prize thus far, 5 of them are based in Hong Kong, so hosting this event in Hong Kong has a particular significance to many of us here. In the past 2 days, we have organized the Enlightening Science and Technology Forum and the 2024 Asian Young Scientists Fellowship Annual Conference. The first one in the Hong Kong University of Science and Technology and the Asian Young Scientists Fellowship Annual Conference yesterday at the University of Hong Kong. The Future Science Prize Week will have many more exciting programs to come in the following 3 days, from November 1st today to November the 3rd. Starting from today, we will have a 2-day science symposium that brings together top researchers from home and abroad, focusing on 5 key areas: chemistry, life science, physics, mathematics, and computer science, during which participants will share the latest cutting-edge research results. On November the 3rd, we shall have a dialogue section in which science-loving and passionate young people will have the opportunity for a face-to-face encounter and dialogue with our future science laureates, followed by the award ceremony at the Hong Kong Convention and Exhibition Center that will be the highlight of the week. Promoting science to achieve the future encapsulates our mission to harnessing the power of scientific knowledge and innovation as a driving force for shaping a brighter future and a brighter tomorrow. The Future Science Prize Week aims to highlight outstanding achievements in science, as well to promote the spirit of science. We strive to kindle the spark of curiosity in people of all ages, especially those in the next generation, our young people, to cultivate a passion for science and an eagerness to support scientific endeavors and to engage in scientific pursuits. I'm most grateful for the efforts and contributions of our committee members, section chairs, keynote speakers, panelists, our sponsors, and also our attendees. I would also like to thank our partners and supporting organizations in the mainland and in Hong Kong, particularly the Innovation, Technology and Industry Bureau, for their tremendous and generous support, and of course to the Hong Kong Science Museum and the Cultural and Leisure Department. I wish all of you a most enjoyable and inspiring Future Science Prize Week. So thank you very much. Thank you.
Thank you so much, Professor Yan. Please be seated. Thank you very much. Now we would like to invite Professor Xuan Dong, Secretary for Innovation, Technology and Industry Bureau, the government of the Hong Kong Special Administrative Region, to deliver an opening remarks. Professor Xuan, please.
Women, Nisa, Professor Lin, Professor List, distinguished guests, ladies and gentlemen, good morning. On behalf of the Hong Kong SAR government, I would like to extend my very warm welcome to all the scientists and speakers who are joining us for the 2024 Future Science Prize Week in Hong Kong. Last year, the Future Science Prize Week, or FSP for short, FSP Week, was held for the first time in Hong Kong, and it was an unprecedented success. Building on this fruitful experience, the Future Science Award Foundation and the Hong Kong Academy of Science jointly organized the FSP events in Hong Kong again this year, under the theme, Shining a Light on the Future of Science, bringing us with more new and exciting elements to the series of events. The Hong Kong Science Museum, where we are now, is one of the most popular museums in Hong Kong. Here, many younger generations, first exposed to science, sparking curiosity and igniting inquisitive minds, making it a perfect venue for today's opening ceremony and science symposium. To further promote popularization of science, the museum is also staging the 2024 The Future Science Prize exhibition, showcasing the research journey and achievements of the laureates, including our top-notch Hong Kong scientists. Indeed, we are blessed to have a wealth of great scientists and academics in Hong Kong who provide solid support for Hong Kong's journey towards our goal of becoming an international innovation and technology center, or INT center here, and an international hub for high-caliber talents. Just 2 weeks ago, our Chief Executive, Mr. John Lee, delivered his 2024 policy address, where a number of new initiatives were outlined to further promote our INT development in Hong Kong. We will adhere to the principle of promoting technology with talents, leading industries with technology, and attracting talents with industry, and continue to perfect the INT ecosystem and enlarge our talent pool. Under one country, two systems, Hong Kong enjoys distinctive advantage of enjoying strong support from our motherland and being closely connected to the world, which is conducive to our global INT collaboration. The Hong Kong SAR government will continue to support the world-class INT events, just like FSP Week right here, and promote international INT exchange and the funds and technology for all to foster a favorable INT center in Hong Kong. Today's symposium will soon begin with the chemistry session. As Nobel laureate Marie Curie once said, "Nothing in life is to be feared. It is only to be understood." The scientific breakthroughs and achievements of our scientists provide us with a deeper understanding of the mysterious and unknown world. I believe that exchanges among scientists today will bring new insights and innovations, much like the transformative power of chemistry. I also hope that this event will become a beacon of light for our next generation. Before I close, I would like to thank Vivian and the organizing committee for orchestrating this impressive event. Please also join me in applauding the 2024 prize winner and our distinguished guest speakers. I wish you all a wonderful stay in Hong Kong and a rewarding exchange today. Thank you very much.
Thank you so much, Professor Sun. Please stay with us. Please stay with us, 请留步。 Please stay with us because we're going to have photo together. Thank you so much for your tremendous support. And before the group photo, just a warm reminder, you can take out your badge, then we can have an even better photo. Yeah, it will look even better, trust me. And then now we are going to invite more guests to the stage to join Professor Sun. Professor Dennis Low, Miss Lisa Leung, Professor Vivian Yam. Continue your big hands to welcome our guests. Professor Lynn Douglas Nelson Cho, Professor Benjamin List, Professor Tony Mock, Professor Catherine Shah, Professor Chui Yi, Professor Anne Ferguson Smith, wow, today we have so many great minds, and then we are so excited to listen to all the sharing. And then Professor Lawrence Judah. We are so thrilled to have many guests travel to Hong Kong. Dr. Huang Xinyuan, Professor Nakajima Hidaku, Professor Tang Jinyao, and Professor Chen Peng. Thank you so much for joining us today. Thank you. Okay, now let's get ready. We can stand closer, and then please have a look to the center. Okay, one step to the left, right? May I invite you one step to the left, please? Okay, looks good? Okay, please have a look to our official photographer. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, a few more to go. And then please have a look, continue to have a look to the center, please. Because we have so many cameras today, so after seeing the center, please also have a look to the, center, continue the center, please. 1, 2, 3, 1. Okay, have a look to the left, please. Yeah, we'll keep rolling. Okay. Okay, thank you so much. Thank you very much. May I now invite Professor Sun, Professor Dennis Low, and Ms. Lisa Leung please remain on the stage for the next photo. For the other guests, please be seated. Thank you very much. And then we are very happy to have many guests join us. We're going to invite 2024 Future Science Prize laureate, Professor Zhang Tao. And also Professor Li Yadong. Thank you for joining us. We're so thrilled to see you. And also, we are very happy to have many VIPs join us today, including Mr. Lee Kwok Pun Ivan, Mr. Zheng Kwok Chai Eddie, Mr. Lee Wai Guan Lawrence, Mr. Choi Chi Man Samuel, Professor Wong Kam Fai William, Mr. Lam Jun Sheng, Dr. Hu Zhang Hong, Mr. Zhang Chi Sham Thomas, Mr. Zhang Ho Lai Jimmy, Professor Mok Ai Ming, Ms. Kwang Si Yin Amy, Professor Tam Kwong Hung Paul. And also Professor Xie Zuowei. And Professor Lo Chak-shing. Thank you so much for joining us today. Thank you very much. Okay. Okay, now please have a look to the center. Please have look at our official photographer. 1, 2, 3, 1, 2, 3. Few more to go. Okay, 1, 2, 3. Yeah, please have a look to the center. One more to go. 1, 2, 3. Okay. Please don't forget your big smile. And then, yeah, one more to go in the middle. And then please have a look to the left, please. Left, we have different angle to tell people our news and our events, and have a look to the right too. Yes, to the right too, we have some camera over there. Okay, all done? Thank you. Thank you so much. May I now invite Professor Sun, Professor Dallas Low, and Ms. Lisa Lam. Please remain on stage for the next photo. For the other guests, please be seated. Thank you. And next, we are going to invite more VIPs join us. Ms. Li Yi Yang. May I invite Ms. Li Yi Yang. Professor Anderson Shum. Ms. Yan Kin Fun Alice. Mr. Chan Kin Tak Samuel. Yeah, don't miss your big hands to welcome our guests, our hospitality. Ms. Wu Lai Wen. Dr. Yim Chi Sheng. We invite Dr. Yim Chi Sheng and also Professor Zhang Guangting Tim, Professor Shen Zhuojun Max, Miss Emily Liao, Miss Ellen Lim, Mr. Richard Liu, Mr. Dan Gong. We invite Mr. Dan Gong. Mr. Tong Hefeng. Professor Li Wenzhang. And last but not least, Ms. Kathy Wu. Okay, so may I invite one step to the left. Yes, perfect. This is just like our spirit. We even always want to strive for the best, even for the photo, just like our science spirit. Okay, please have a look to the center. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, a few more to go. 1, 2, 3. 1, 2, 3. Okay. Keep smiling. Don't forget your big smile. Okay, one more to go to the middle. And then have a look to the right. Have a look to the right, please. Yeah, you can chase him as well. Okay. Thank you so much. Thank you very much. May I invite you, please be seated. Thank you so much. So now, may I invite you all, please return to your seats, because we are going to have the group photo with all of you. So just remain on your seats. We're going to have 2 photos. The first photo, just wear your big smile. The second photo, we will have another gesture. So please get ready. Please be seated. Yeah, and then for those who are wearing glasses, you can adjust a little bit to look even more stunning. Okay. So let's get ready fast. Okay, which camera we should look at first? You are all the stars. Yeah. Okay, so, okay, we have just a moment. We cannot miss anyone. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, few more to go. Please have a look to the center. Don't forget your big smile. 1, 2, 3, 1, 2, 3. Okay, continue to have a look to the center, please. Okay, now we have another photo with your thumbs up to boost the energy to make our science symposium even more successful. Okay, give a like to our science symposium. Yeah, thumbs up. Okay, one more to go to the middle. Is it okay? Okay, thank you very much. Thank you so much. Thank you very much for joining us today. Thank you. So after the opening ceremony, we are going to have the upcoming session will be about chemistry, the central science towards interdisciplinary research. I would like to introduce with you Professor Vivian Wing-Wah Yam as this session's convener. She is the Philip Wong Wilson Wong Professor in Chemistry and Energy and the Chair Professor of Chemistry, the University of Hong Kong, member, Chinese Academy of Sciences, Foreign Associate, U.S. National Academy of Sciences, Fellow, World Academy of Sciences, founding member, Hong Kong Academy of Sciences, co-chair, Program Committee of the Future Science Prize Week 2024. Please give warm welcome to Professor Vivian Wing-Wah Yam.
Good morning, distinguished guests, ladies and gentlemen. It is my great honor to serve as the chemistry section chair to convene today's section and to see you in Hong Kong. First, I would like to extend my sincere welcome and gratitude to all of you. Thanks to the elaborate preparation of all our speakers and the effort of the organizers. I believe you will have an inspiring and enjoyable scientific section on chemistry. The topic of today's section is the central science towards interdisciplinary research. We have 4 speakers today. They are Professor Benjamin List, Professor Yi Cui, Professor Pang Chan, and Professor Jin-Yao Tang. So let me introduce the first speaker. The first speaker is Professor Benjamin List from the Max Planck Institute for Coal Research. In 2021, he received the Nobel Prize for his work on asymmetric organocatalysis. Today, he will bring us a fascinating talk about the universality of acid catalysis. So, can we invite Professor Benjamin List, please?
Wonderful. Thank you so much, Vivian. I'm always full of excitement when I have the chance to come to China, but Hong Kong, this is even more exciting. I feel the enthusiasm here, and this is coming from old Europe, always a great pleasure to be here, and I wanted to thank you, Vivian, for having me here today. So I would like to start out with my by far biggest inspiration. And my biggest inspiration is a chemical transformation that would be shown on the next slide. And it is actually photosynthesis. And I don't know how you feel about it, but for me, this transformation, which happens in the leaves of plants, this is a special type of plant, the moss, where CO2 and water, 2 of the most abundant and readily available and inexpensive material on this planet, are united with sunlight This is a thermodynamically uphill reaction. It needs energy, and light provides that energy to give, on the one hand, carbohydrates, like glucose, for example, a complex hexamer. And carbohydrates are the basis of all food we eat on this planet, in case you haven't known this. And as a byproduct, as a stoichiometric byproduct, as chemists like to say, oxygen is produced, the single source of the air we need to breathe. So two of the most important ingredients for our life are created in this one chemical transformation. Really, really remarkable. And I would claim here, this is probably the most important chemical reaction, chemical transformation, I should say, happening in our solar system. But it doesn't happen spontaneously, right? CO2 and water do not react in the presence of sunlight to give carbohydrate and oxygen spontaneously. It requires the help of enzymes. And enzymes are proteins that occur in our bodies and in all living beings, which are catalysts. And this conveniently brings me to my favorite topic, and that is catalysis. And catalysis, I think, even for those who are not chemists, is the true transformative power of chemistry, as Professor Sun has mentioned before, because catalysis basically enables chemical reaction to occur. For example, A and B unite to give C by reducing the activation barrier. When you bring two molecules together, it requires a little bit of energy, and the catalyst can lower that energy and facilitate this chemical process, make it possible in the first place, in fact. But the special thing about catalysts is that in this chemical process, they're not being used up. The catalyst mediates the chemistry, but it is not itself converted into something else in it. And that, in turn, means a catalyst can do its job an infinite number of times. A single molecule of magic, as I like to say. You know, without the catalyst, nothing would happen, but with one single molecule of a catalyst, a huge amount of something valuable can be created. And that is the true power of catalysis. And this has led to the situation, actually, that catalysis is not only arguably the most fascinating science. I'm sorry, I hope I'm not insulting anybody, but I cannot understand how anybody can research something else than catalysis. It's my personal flavor. But also quite a relevant technology. I would argue, but challenge me if I'm wrong, that catalysis is the single most important technology for our human life on this planet. And there is no other technology that can claim to feed, to heal, to warm, to transport humanity in our goods, other than catalysis. And I think it's not shown here, but catalysis for the economically inclined people contributes to 1/3 of the global domestic product. Numbers in the trillions. As I said, I think the most important technology available. And I just wanted to give you one example of all these incredibly relevant transformations that chemists have developed over the years. And that is actually Fischer-Tropsch. Sorry, it's cracking, not Fischer-Tropsch. It's another way how to make gasoline. It's cracking. And cracking is actually the catalytic cracking, the process how we make fuels, gasoline, that transport us, our ships, our planes, traditionally our cars also. And cracking is done on an up to 1 billion ton scale, huge amount of crude oil products that are distilled and then cracked, form these hydrocarbon compounds, olefins and alkanes, in an incredibly large amount, and fuel our industry. And this is just one of the many examples that contribute to our global domestic product. I also would like to emphasize Haber-Bosch, with which fertilizers are made. And without Haber-Bosch, there would only be half of you in this room, because we couldn't feed 8 billion people on the planet. Oswald, of course, is important, and Ziegler-Natter, which was also discovered at my institute, the way how we make plastic is one of the most important chemical reactions that chemists are doing on the planet. Now, the interesting thing about this has been for a long time that chemists believed in all of these transformations we need metals as the key catalyst component. And this is also nicely reflected in the Nobel Prizes that have been given over 100 years, actually from 1909 until 2010. There had been, I think, 8 or 9 Nobel Prizes in the area of chemical catalysis. And literally all of these awardees received the Nobel Prize for work using metals as the catalytic principle. And that is something that, as a graduate student and later as a postdoc, surprised me a little bit, because it turns out that the enzymes that I've mentioned in the beginning of my talk, that nature has evolved to catalyze biological chemical reactions, those enzymes do not need metals as the active principle. There are definitely many metals that use metals, but not all of them. In fact, the majority of all enzymes are completely metal-free. And so with that inspiration, I found that proline, an amino acid, in a way kind of a simplified enzyme, a purely organic molecule readily available from nature, inexpensive, non-toxic, both enantiomeric forms are available. We make it even in our own body, can catalyze a very challenging aldol reaction. At the time, this was actually one of the most sought after chemical transformation, the direct asymmetric aldol reaction. The best groups in the world were working on it in Stanford, in Tokyo, in China, everywhere. People were trying this. And it turns out this simple, purely organic small molecule not only catalyzes this reaction, but it defined the state of the art. In fact, until today, some of these reactions are best catalyzed with proline. And that was kind of, in the beginning, it was kind of a bit sort of a surprise to the community, and people were rubbing their eyes and oh, like, interesting, a bit maybe the exception of the rule that we always need metals. And there was also criticism about the high catalyst loading. I mentioned a single molecule away from magic, but we needed one molecule to make 4 product molecules. That's far away from that magic. And that, of course, was criticized. But little by little, people began to realize what a powerful principle organocatalysis could be. And now it's actually the #1 field in asymmetric synthesis. Nowadays, no company in the world, no pharmaceutical, no chemical, no perfume, any company that makes molecules is not using organocatalysis anymore. And this is also true for all academic institutions that have organic chemistry. They're all doing it now. And one of the key contributions to this change has been the discovery of the utilization of this proline-catalyzed aldol reaction in a drug synthesis, the synthesis of darunavir. We all remember, of course, the COVID pandemic, which was horrible, of course. I don't want to downplay it, but there had been an even worse pandemic before in the 1980s. Some of the older people might remember it, HIV, human immune deficiency virus, a virus that is deadly, actually, and most people who get infected with it die from it, and for which there is no vaccine available, in contrast to COVID. But this is now handleable because of the help of pharmaceuticals like darunavir, which are designed by medicinal chemists and which are made by process chemists. And we were, of course, happy to see that this chemistry had found some use on a technical scale. It's just one of the early examples. There are now many, many examples of asymmetric catalysis on a technical scale. But what I wanted to talk about today is the universality of acid catalysis. And acid catalysis, of course, is just one aspect of proline catalysis. Proline is a bifunctional molecule. It's an amino catalyst, but also a Brunstad acid. And what I'm so excited about acid catalysis right now was a simple realization that I had, and that is the vast majority of all chemical reactions can be catalyzed with acids. And there's a very simple reason for that, and that is all that acids need as the key element in their substrate is the existence of electron density. And I don't know if you know this, but all materials, all molecules, all substances, every matter on this planet contains electron density. And so there is this potential for universality if one had good acid catalysts. And in addition to this, we can easily modulate the reactivity. So this is well known, of course, with the Brunstad law. This is a law that was created by a Swedish chemist, Brunstad, I think over 100 years ago, basically correlating the acid strength, and we all know acids, some are very strong and they can dissolve metals, with the reactivity in a catalytic reaction. And of course, as you might imagine, the stronger the acid, the higher the reactivity. The problem, though, comes from the selectivity that we also need in chemical reactions, right? We want to catalyze chemical reactions, but not randomly. We want to get one specific product, ideally one single stereoisomer. And that problem comes from the fact that, you know, a proton is simple, small elemental particle. It's a sphere, it's tiny, and it can never induce any selectivity in a chemical reaction. So this is the reason why people, and this is an example from my laboratory, developed, inspired by the work of David Evans and of course many others before me, people developed Lewis acid catalysts, in this case copper triflate, and in order to bring in selectivity, they coordinate a chiral complex ligand around that metal. And then you have a selective acid catalyst, a Lewis acid catalyst. But the problem of this design, and it's an inherent problem that had been overlooked actually, that this ligand, in turn, is a Lewis base. So basically you mix an acid and a base, and that weakens again the acidity, the Lewis acidity in this case, and you have a weaker catalyst. And that is why you again need very high catalyst loadings. And in addition, you need to decorate your substrate. In this case, it's a ketone reduction with various activating groups, an arene, another ester group, a tert-butyl ester. Here you need a special reagent. And all these requirements, of course, limit the scope of this type of catalysis. And so we had recently, actually in 2016, a breakthrough in my group. Actually, it started in 2012, when we designed such dimeric imidodiphosphate type catalysts. And those catalysts have an acidic proton in the middle of them, right here. And then around that proton, we have created a chiral small molecule-based cavity that, like an enzyme, provides a confined active space in which a chemical reaction can occur. And the beauty of this design is that we can, by modifying this inner core substituents, oxygen to N-trifluryl, we can drastically vary the acidity. Here you have some common Bronsted acids. Sulfuric acid, for example, you might remember from high school. It's a very strong acid that can dissolve many metals. Very dangerous. You should never come in contact with sulfuric acid. pKa is roughly 7.6. Our acids are 1,000 times stronger, actually, this one here. And we can go even beyond that, reaching the acidity of those acids that people have called magic acids, the strongest acids that are known to chemists. Very, very reactive species, but also confined. They have this nice chiral active volume around them, enabling selectivity to be dialed in. And so I wanted to show you a few examples. I know some of you are not chemists, many of you probably, but I still wanted to share with you a few of these reactions that we can catalyze with these acids to illustrate the universality of this principle and the power of what these kind of catalysts can do nowadays. For example, Han-Yong Bae and I, we discovered an aldol reaction now where we don't use 25 mole percent, so one molecule makes 4 new product molecules, but we use ppm level. That means 1 part per million. And in some cases, we could even go lower than 1 part per million, reaching kind of ppb type asymmetric catalysis, the lowest catalyst loading that has ever been used in any asymmetric catalytic carbon-carbon bond-forming transformation. And what that means for the economists here, 1 kilogram of such a catalyst could be used to make a megamole. In this case, this would amount to 388 tons of a product. The global demand of a blockbuster drug would be in that kind of range. So you get a feeling of how powerful organocatalysis has become. Also, with Hui Zhou, she's now a professor at Wuhan, we found that these catalysts not only feature this high reactivity, but also a remarkable selectivity when it comes to unprivileged small substrates like 2-butanone in a hydrocyanation reaction. This is an interesting reaction because it can be catalyzed by enzymes, by metals, and by organocatalysts, but even engineered enzymes, the most sophisticated catalysts that humans can make and modify, cannot improve the enantioselectivity beyond what Hui Zhou has achieved and that we have just published a couple of years ago in a Nature paper. Moreover, we can catalyze chemical reactions that were previously considered impossible. The Narel to isopipetinol conversion, for example, was for 100 years considered an impossible chemical reaction for the simple reason that the product is more sensitive to acids than the starting material. Right? Acids are universal, and they can also, in principle, activate this one. But because of the confinement of our catalyst, the reaction stops after the cyclization to this extremely valuable product which now can be used to make menthol. Menthol has been made for over 100 years on a technical scale using chemical synthesis, but this route is, by definition, the shortest that has ever been realized. Moreover, we can make cannabinoids. I'm not sure about the legal status in China and in Hong Kong. In Europe and in Germany, at least, they're now being legalized. They're used as pharmaceuticals, for example, but also recreationally for relaxation, I guess. I've never tried these compounds. But we can now make them synthetically in a very straightforward two-step route, and there's $1 billion market for all of these three molecules shown here. And the almost last example is an application in whale chemistry. You might be a little bit surprised. The sperm whales are beautiful animals, probably also around Hong Kong. And the sperm whales, actually, they are not very good in eating. And that is because they have only this big mouth, and then they open the mouth, and all the food comes in, but they cannot select the food, right? And what happens is they eat squid, and the squid has some bones, and the beak also. They cannot digest, and it accumulates in their intestines. And what happens is they form these waxy-like rocks, and they can die from them, actually, sometimes, but also they can get rid of them sometimes. They lose these rocks. They swim on the ocean for a few years, sometimes decades, and then a fisherman finds them. This is a fisherman in Thailand, and he found this rock here, which weighs 3 kilograms, and they gave him $3 million for that rock. And why? Because the amazing thing, given its history, squid, whale intestine, and then sort of excretion, if you break this rock apart, you experience the most beautiful scent that you have ever experienced, and that's the scent of ambergris. And ambergris has as the specific component the key ingredient ambrox. And ambrox is this molecule here. And these rocks are so valuable because for hundreds of years, chemists were unable to make ambrox in a really competitive manner. And so we have now accomplished this. Just earlier this year, we have published the first catalytic asymmetric polyene cyclization of homofarnesol, which is this simple compound here, which BASF, a big chemical producer, the biggest in the world actually in Germany, they can make very readily, and we can catalyze now for the very first time with an organic small molecule catalyst, its cyclization to this beautiful and extremely valuable molecule. So with all these nice results, at some point I said to my group, how about we protonate alkanes? You know, very much like in cracking, the first chemical reaction I showed you today. Can we go ahead and protonate an alkane, maybe site selectively so, and then cleave to, you know, just the desired small molecule fragments? That was the idea, and again, people would say, yeah, it's kind of a almost crazy idea. How is that possible? Such a transformation, how do you protonate an alkane in the first place? Such a transformation would involve a carbon with 5 bonds to it. And if you're not careful and propose this to a German organic chemistry professor as a student, you will be kicked out of the examination immediately because they don't accept that concept, right? And on the internet, they would make fun of you and call this a Texas carbon because it's obviously wrong. You cannot draw a carbon with 5 bonds. But it's also somewhat ignorant because actually George Olah received a Nobel Prize in 1994 for his work on carbonium ion chemistry, as these compounds are called. So they are actually real, and he has shown these compounds exist. And so the idea then, of course, was, can we control the selectivity in hydrocarbon alkane cleavage with our ID-Pi catalysts? And I was telling my students, the day we will reach this goal, then I can retire. And that was maybe a decade ago or so. And unfortunately for me now, actually this is possible. And I have a little group at Hokkaido University at ICRAD, and we have now published our first science paper together where we could show actually we can enantioselectively cleave such hydrocarbon, purely hydrocarbon alkanes, first example of that type, where small organic molecules activate alkanes to give these branched olefins here in excellent enantioselectivity. So this paper was just came out. So now I have a problem because I told them I will retire, but officially I still have at least 15 years or so to go, so I have to come up with a new idea. And I wanted to share this idea with you Right now, we are sort of in a very early phase, and it's just sort of an idea. And it all centers around my fascination with photosynthesis. I don't know if you know this, but there are bamboo trees that grow, I think, 1 meter in a week or so. So they're incredibly amazing, because if you think about it, this material all comes from the CO2 from the air, right? There's 420 parts per million of CO2 in the air, and that is the source of all this matter that you see there sort of precipitating out of thin air. Just remarkable. And again, this is the chemical reaction. CO2 reacts with water to give carbohydrates that form the wood and all the other stuff, the plants, the leaves, and so on, and oxygen. They give us the oxygen we breathe. So the question is, this is happening on a 200 billion ton scale, in case you didn't know this, every year. In spring, the plants start to build their leaves on a 200 billion ton scale. Unfortunately then, in the end of the year, the leaves fall down, they rot again, and they form CO2 again with the organisms that digest it. So that's what photosynthesis does. Can we chemists develop an artificial photosynthesis that simulates kind of this process? And in its essence, the question arose for me, and I was surprised to find nobody else has really thought about this before, at least, I mean, not in the mainstream. And the question was, can we then split CO2 directly? Can we split CO2 into carbon and oxygen? I think that would be a nice and really challenging transformation. I hope I can inspire the next generation in thinking about this. I know it's a bit awkward. Maybe some of you think this is a crazy idea. How can you do this? This is obviously thermodynamically uphill. And we all know that carbon can be burns in the presence of oxygen to give CO2, right? So the reverse reaction is well known to us. How can you go in this direction? But my answer to this is, I can only cite Steve Jobs, who had said, people who are crazy enough to think they can change the world are the ones that do, right? So I would say in my language, a crazy idea is a minimal requirement for a revolutionary discovery, right? If it's mainstream, by definition, it cannot lead to a scientific revolution, right? So it's kind of a minimal requirement, but unfortunately, it's not a sufficient requirement. So it could also be a crazy and unfortunately stupid idea, right? So you're always sort of in this fine balance here. However, we have done the computation, and it's actually simple to do, of course. It turns out that this transformation, for example, to graphite and oxygen, requires a large amount of energy, I admit, 94.2 kcal per mole. But this is actually less than what is needed for photosynthesis. Photosynthesis requires more than 120 kcal per mole. So you cannot convince me that this reaction is impossible. It must be possible. And as another element of encouragement, the reaction is already happening while we are speaking. It's happening on Mars, and actually also in the outer part of our atmosphere. And the question for a long time had been, why is there oxygen on Mars? There's very little oxygen, but there is oxygen on Mars. And the question was, how does it form? Because there are no plants on Mars, at least not to our knowledge. And the theory was that perhaps CO2 in the atmosphere of Mars is somehow split into carbon and oxygen. And also there's a second pathway into carbon monoxide and oxygen atoms. And this was experimentally verified 10 years ago. So this transformation happens on a much higher energy level, 11.44 electron volts is required, but you also generate oxygen in an excited state, and carbon also in an excited state. So that's why this large amount of energy is required. And our idea now is to catalyze this chemical reaction. And I know it's a bit of a crazy idea, but as I said, you need a crazy idea. Organocatalysis was a crazy idea too when I started out, and I have a similar feeling right now. And so what would be appealing about this transformation is we could stop climate change by picking up CO2 from the atmosphere. We could use the coal to generate energy. The technology is around, right? We know very well how to create energy from coal. And we could transform the chemical industry into a sustainable chemical industry by utilizing solar carbon to drive it. So that's my idea with which I wanted to finish. And I'm very happy that a big German foundation, the Werner Siemens Stiftung, they're located in Switzerland, are now supporting us with a huge donation. And for 10 years now, we have enough funding to investigate this question. And I would be super happy if all of you work on this, and if you discover this transformation. If we are discovering, I would be slightly happier because it would bring some new meaning to our old-fashioned name, the Max Planck Institute for Kohlenforschung. It means coal research, as Vivian has translated it. We never translate it, but nobody's doing coal research anymore at our institute. But if we make coal again, I think that would be, useful and to our naming. With that, let me thank the great team that I work with. They're from all over the world. There's always, I think now we're 1/3 Chinese people, and I love to work with them. I had people from Hong Kong, actually, and I love the enthusiasm, the passion for science that people have here and that I witnessed today. And I would like to thank them, the funding bodies that have supported us over the years, and all of you for your kind attention. Thank you so much for having me.
So thank you so much. Thank you very much for the very exciting and inspiring talk by Professor Benjamin Liss. So particularly, it's really gratifying to see how chemists is going to change the world. And we look forward to the photosynthesis with the new catalysts that you are working on. And everyone will be joining to do this. So let me introduce our second speaker today, Professor Yi Cui. Professor Yi Cui is the director of the Precourt Institute for Energy, founding director of Sustainability Accelerator, Fortinan Founders Professor of Material Science and Engineering, and Energy Science and Engineering from Stanford University. And today, Professor Cui will be telling us about reinventing batteries. That's very important. Thank you.
Thank you, Vivian. Very exciting talk, Professor Liss. That's a really good catalytic reaction session. This really fits very well for this year's Future Science Prize. We have two winners for physical science, Professor Zhang Tao and Professor Li Yadong, for winning the award based on their work in single atom catalysis. Now let me switch gear a little bit, but still falling into the domain of chemistry. Professor Liss is telling you, hey, atom-atom reaction, molecule-molecule reaction, building chemical bond, transfer the electron, forming that chemical bond. Now the topic of batteries is taking this chemical reaction, utilized in a fundamentally very different way. Instead of having the electron forming the bonding, you are actually taking the electrons, going to outside circuit, and doing the work, and come back to form the bonding. That's why you need to separate one full reactions into two half reactions. For students right here, this is the fundamental of electrochemistry, separating the path of how the electrons move and how atoms move, and into two half reactions. So this is driving by the really fundamental ideas. How could you use clean electricity to power the whole society? Falling into two categories of application. One is mobile, the mobility, cell phone, laptops, electrical cars, electrical plane even, may be possible in the future. The second is in the bottom is stationary energy storage, store electricity coming from solar and wind, integrating with electrical grid. These two applications really driving in the future, no surprise, each area will be $1 trillion market. So we all know 2019 Nobel Prize was given to these three pioneers developing lithium-ion batteries, using lithium ions as the cations to neutralize electrons, really bring up the mobility revolution. And then we ask the questions, what's next? Is it all done by lithium ion? The answer is no. So we are still trying to look for how much more energy we can pack into given size, whether it's by weight or by volume. Can you double or 4 times of current batteries technology? Can you really have much longer lifetime? Instead of a couple of thousand cycles, you go to about 5x to 10x more cycle life. Instead of 5 to 10 years, do you have never die batteries, let's say 30 years? This is necessary for grid-scale energy storage. What about fast charging? Can you charge within 10 minutes or 5 minutes? This is really means you're driving electrons. You're driving the movement of ions very, very fast. Again, coming back to the kinetics of the chemistry or electrochemistry. And can you enable complete safety? Batteries still burn. And for the very large energy storage system, this becomes a big, big challenge. The reliability of the electricity grid is not there, and the safety concern is there. And the cost, can we generate technologies that provide 10x lower cost compared to the current lithium ion? Get to about $10 per kilowatt hour. Then you can have seasonal storage. You can have storage everywhere. Truly enable the green electricity revolution. At the end of the day, anything go to the global scale require you think about materials availability, circularity. Professor Liz was telling you some of the big number right there, billion-ton scale oil and gas industry. Billion tons is going to be the unit for you to go to global scale. The current lithium-ion battery production, we are only talking about 5 million ton yearly production. We are about 3 orders of magnitude away. But how do we obtain so much lithium, so much cobalt, nickel, and so on? That's not a trivial question. This requires new abundant chemistry. Need to think about circularity. With these challenges in mind, maybe let me share with you in the next about 25 minutes, how do we work on this problem? Let's select a couple of problems to highlight today. First is, how much more energy can we store given certain weight, given volume of the batteries? So the Nobel Prize winning work, 2019, was built on 50 years ago of intercalation chemistry. You put the lithium in and out into a crystal structure in a very reversible way, causing very small disturbance to these materials, to this chemistry. But to store a lot more energy, you will need to consider new mechanisms that go beyond intercalation. This might include alloying. This might include plating and stripping. This includes complete chemical transformation called conversion right here. This is fundamentally very, very different from intercalation chemistry. It's so much harder to handle. So in my lab, past 19 years at Stanford, we took on this challenge and really start to look into new materials. They can store 10 times more charges compared to the intercalation chemistry. But they represent very, very big challenges. How do you do the alloy reaction? How do you do the conversion reactions? So let me show you by examples. Graphite is used in existing lithium ion. Based on intercalation of lithium between the graphene plane, this offers you 370 milliamp per gram of capacity. But if you could enable silicon to alloy with lithium or metallic lithium based on stripping and deposition mechanism, you have 10 times more charge storage capacity compared to graphite. This allows you to store a lot more energy. Similar on the positive electrode side, cathode. These are the current materials, lithium cobalt oxide, crystal structure, lithium manganese oxide spinel. and the lithium iron phosphate, these are the foundational materials enabling lithium ion batteries. And if you could go into conversion reaction that sulfur, lithium 2S offer you about 10x of charge storage capacity. These are the materials make it possible with current lithium-ion battery energy density 250 watt per kilogram, all the way go up to maybe 1,000. We are talking about 4 times of energy density improvement. We are talking about for the same size of the batteries. Instead of 300 miles car you are driving, it can go to 1,000 miles. We are talking about the possibility of having electrical flight, at least on a continental flight. Across the ocean might be harder. Within 5-6 hours, this could all be electrified. So the impact could be really big if this possibility can be enabled. So let me come to the first example. When I joined the Stanford faculty in 2005, start to look into the battery problem. And silicon really come to my attention right away. It's 11 times of charge storage capacity of graphite, but its volume expansion is very, very big. It's 4 times. Once you put lithium in, it breaks nearly anything. And anything expands by 4 times in solid state. And this material, this chemistry, all these problems start to show up, and how to avoid breaking, and how do you build stable interface between each of these particles with organic electrolyte. Lithium alloy with silicon carries so much reduction power to reduce nearly any organic solvent in contact with this electrode. How do you build a stable interface? In 2008, we published the first paper really taking the approach of nanoscience, designing the materials with the size scale, with the surface and interface, which can handle the problem of volume expansion and breaking, and also instability of the interface. So this was my first paper published, and this has turned out to be the first paper really starting the whole research field of nanoscience design for the batteries. So we also developed tools as well to really try to understand what happened on these materials. What happened to this material? What happened on the interface? This is a transmission electron microscopy holder, and we built in this situ electrical biasing. You can pass in current through the materials, building a single nanowire batteries inside transmission electron microscope. This technique not only allows us to look at this nanowire structure, but also having this particle can be connected to these wires. And these nanostructures right here really offer small enough size for us to understand size dependence, breaking behavior. And let me share with you a few of these videos. And this is one of the videos of these nanowires, roughly with 200 nanometer in diameters. Once lithium coming in, the volume expansion is taking place. And this wire is coated with copper on the surface. And the copper is broken, but this nanowire is not. So below certain size, the solid state material do not break that easily. Let me share with you a broken, I don't know how do I play this video. Can somebody in the background and click on that video, then it's going to play. Somehow here I cannot click on. And you move the cursor to that picture. And then you click on that picture. Well, perhaps it doesn't work, but you need to trust me. There's a breaking behavior happening. It's good. It's a beautiful movie right here. And utilizing this video and transmission electron microscopy, we could identify what's the breaking size. That's guiding the materials design to avoid the breaking. So over the years, Okay, so this is showing the central particle right there. It's about 800 nanometer to start with. And this one, crystalline silicon core is shrinking. This forming lithium silicon alloy amorphous shell. Eventually, this particle is too big to really hold, to relax the stress, and it will be broken. Once it's broken, you are losing materials, you are losing your lithium storage materials, then the capacity is decay. So this battery's capacity decay is very, very fast, and based on this alloy mechanism. So using nanoscale design, we were able to, over the years, starting from nanowires, to relax the strain, to avoid the breaking. And we have been through about 12 generations of design because there are other problems right there. Interfacial stability, how do we handle that? There's another breakthrough concept is using double wall hollow structure that force silicon volume expansion towards the empty space inside. Then you can build stable solid electrolyte interface. So with all this understanding, we believe we are getting close to the final stage of solving all the problems related to silicon. And 2008, I founded my first startup company, Amprius, and really taking the idea from the lab and doing further development and manufacturing. Amprius is right now having the world's highest energy density batteries, supplying to the Airbus commercial drone. This commercial drone right here flying in 70,000 feet high and continues for 25 days, breaking the world record. In 2022, the company and the US part went for IPO and New York Stock Exchange, now raising the capital, try to build further the largest scale manufacturing plant. This is the picture, the whole board of directors. We are in the bell ringing event. That was me right there. And so the challenges for manufacturing from commercial just started actually IPO. IPO is not the end of commercialization. It's the new beginning of the scale-up production. So after silicon, we need to look at lithium metal anode. This is based on deposition and stripping mechanism. Lithium metal anode is considered the holy grail of the battery research. It gives you the ultimate energy density per weight. And in the 1970s, that was even before I was born, scientists were trying to enable lithium metal, but it was not possible. That leads to the development of lithium-ion battery using intercalation instead of using metallic lithium anode. Based on the deposition and stripping mechanism, you take a lithium foil, you are going to react with organic electrolyte, generating this interfacial layer. But deposition cannot be guaranteed to be a very flat layer by layer deposition. You are causing surface curvature change. This break, this SEI layer, solid electrolyte interface, causing the hot spot, growing this filamental, we often call dendritic structure, lithium dendrite. This will go to the other side of the electrode, cause the battery shorting and catching fire. During stripping, there's no guarantee you strip from top to bottom. You must strip from the bottom because you take electrons away, you take lithium away, you lose control in stripping. And you can cause this dead lithium formation. So this has been half a century long old problem. How do we solve this? In 2017, my lab analyzing this and really narrowed down to the root causes of the problem. One is high chemical reactivity of lithium. The other is plating and stripping cause such a big volume fluctuation. These two coupling together, one is the yin, the other is yang, really coupled together cause all the surrounding problems. Very, very hard to handle. So at Stanford in around 2015, when Steve Chu stepped down as the Secretary of Energy from that position, from Obama administration, we started to collaborate, and we innovate for the first time the whole concept design of a hollow carbon with CD layer, guided the deposition inside this hollow carbon instead of going everywhere. We also extend this concept further. Instead of using amorphous carbon, this can be graphitic carbon. This provides the mechanical resilience, guided the deposition without causing mechanical breaking, further improve this concept. We also taking the graphene oxide, doing the molten lithium infusion between the graphene oxide layer, offer new type of host materials, hosting, deposition, and stripping without causing large volume fluctuation. And also how this graphene oxide is oriented, whether it's vertically, horizontally, or randomly on the electrode, causing the tortuous path to the different degree to guide the material's deposition. This host concept design turned out to be one of the most important concepts to enable the deposition and stripping chemistry on lithium, on sodium, potassium, and also on other metallic anode. And the second one is with my colleague, Professor Zhenan Bao and Jian Chen, is how do we borrow all this idea in organic chemistry, organic chemical reaction to guide the electrolyte design, guiding the solvent design, putting in, for example, the effect of stereo effect, electronic effect right there by adding fluorine atoms, and also fine-tuning the symmetry of the molecule, the dipole moment, to really now systematically design the electrolyte, having very exciting breakthrough in these areas. Also equally important is the tool development. In 2017, the Nobel Prize was given to cryogenic electron microscopy to solve the protein, solve the biomolecule structure. We actually borrowed the cryo-EM technique and utilized that for the first time to look at very fragile battery materials and really guided the development of the energy material using cryo-EM. These other new tools. We keep learning and borrow that and put it into the battery research field. So this is still ongoing. Now I want to share with you the second big problem we need to solve. And high energy battery is for mobility, but for long duration, stationary energy storage, for solar and wind electricity integration into the grid. This is a multi-time scale problem. For electricity grid right here, you need it to be stable, the voltage needs to be stable, frequency needs to be stable, and you need to have minute-to-minute storage, input and output to stabilize the grid. You also need to carry all the way to seasonal storage. This is really a tough problem. You want to have very safe electrochemistry, never catching fire. You want to have very long lifetime, lasting for 30 years, 30,000 cycles. Then you can do 3 storage cycles per day, continuously for the next 30 years. You want it to be very low cost. Then what's the chemistry available for you to do that? Let's revisit aqueous electrochemistry. We know electrochemistry originated from aqueous solution. It was a recent 30 years when we moved into lithium-ion batteries. That's the organic solvent-based batteries. Before that, it was always aqueous electrochemistry. Aqueous offer you really extreme safety, no catching fire. But what's the longest lifetime chemistry available? We started to look into nickel hydroxide, nickel oxide hydroxide. This is well known for nickel metal hydride, nickel cadmium batteries, and it can run for a very long time, this cathode chemistry. Then we asked the question, if we could take this cathode chemistry and utilize the anode chemistry, that's hydrogen become water, that's half of the fuel cell, and combine these two together, we can construct new type of full battery reaction. Now we call nickel hydrogen gas batteries. So as soon as invented this, we discover NASA in the United States has been using these batteries for Hubble telescope, for International Space Station, out there in the outer space for 30 years already. It's so reliable. This is the proving point, reliability, lifetime of this chemistry is very robust. However, the biggest problem is the cost is too high for NASA technology. They use platinum as catalyst. Now we change to nickel, moly, cobalt. This again, come back to the topic today, catalysis. these catalysts are so important right here to help reducing the cost. So we construct this chemistry, for example, running for 10,000 cycles right there without decay. This is very robust chemistry. And not only that, the nickel one, we also innovate using other metal elements with a 10x low cost. For example, manganese, Mn. And we invented for the first time of a manganese hydrogen gas batteries based on cathode is manganese 2+. Deposition from manganese dioxide solid. Anode is hydrogen become proton back and forth. This beautifully generate very long lifetime manganese hydrogen gas batteries. So 4 years ago, I spun out another company called Innovanio. Innovanio right now is taking this technology, designing it into this real product right here. For example, this one battery cell, the diameter is about 12 centimeters, like this big in diameter. The length is 1.8 meters long. One battery cell stores 3 kilowatt-hour electricity. We are building this unit right now, also building this rack for the largest scale energy storage. Let me highlight the very wide operation temperature window. This is a chemistry based on potassium hydroxide solution. It's a freezing point. It's minus 42 degrees Celsius. So this chemistry can extend from minus 40 to plus 60, working so well. This is what lithium-ion batteries cannot offer. Lithium like to operate at room temperature. Very low is bad, very high also very bad. So, but this is the chemistry now, nickel hydrogen gas battery we can offer, and for the long duration energy storage. So at the end of my talk, let me share with you a very exciting news. 1 month ago, US Department of Energy announcing a DOE Energy Innovation Hub. This is $62.5 million energy hub. I serve as the director of this hub. We just got awarded. This is the hub. We try to look into what would be happening in the next 30 years. We want to look for 10x cost reduction. Extreme safety of the battery chemistry can allow us to go to 200 terawatt-hour scale, billions of tons of materials. There's very few choices right there. We need to look at aqueous chemistry. We need to look at very low cost, redox chemistry, zinc, manganese, iron. Construct new type of battery chemistry for storing large quantity of electricity for seasonal energy storage. So organize a team consists of these 32 scientists right here, coming from 15 institutions. This is led by Stanford University, and I serve as a director. Linda Nassar serves as our chief scientist. Steve Chu is our advisory council chair. We have really very talented folks as a team working together for the next 5 years, try to enable new type of electrochemistry for stationary storage. Let me summarize my talk. These are the guiding challenges has been guiding my research lab in the past 20 years to innovate in these areas. I give you the example of high energy density batteries and one example on grid-scale energy storage. There's a lot more to come to enable the circularity, extreme safety, ultra-fast charging. With that, let me end my talk by thanking the whole research group and Department of Energy for the long-term support. Let me say congratulations to Professor Li Yadong and Zhang Tao again for your Future Science Prize on catalysis. This is the highlight of the whole chemistry. Thank you very much for your attention.
So thank you very much for the wonderful and exciting developments showing us how not only fundamental basic science, but all the translation. And also congratulations on the consortium. So thank you very much. So let's move on to the third lecture. So the third speaker is Professor Peng Chen, the Peter J.W. Debye Professor of Chemistry from Cornell University. And he's going to tell us something different But this is the good thing about chemistry. It's really a central science covering all aspects. Single molecule chemistry, again, very important topic. Professor Chan, please.
Thank you, Vivian, for having me here. And we just heard two beautiful talks, how you can use chemistry to make very important molecules or very important materials. So what I'm going to tell you in the next about 25 minutes is how we can study chemical processes down to single molecule level. And in three different areas. Now, this is all start with the development of optical microscopy over the many years. We probably have seen antique microscopes maybe existing in this particular museum, but with the development of the optical microscopy, now one can purchase such instruments and put into your lab bench and to do or to study fundamental chemistry. One can see individual bacterium cells. One can also see catalyst particles. If you detect fluorescence, one can see individual molecules, or maybe individual molecules in cells. Now, my lab has been using these technical capabilities of studying fundamental chemical processes. So what I will show you today is three short stories about looking at catalysis on nanoparticles, looking at polymerization reactions, and also protein complexes on the surface of bacterial cells. We're talking about catalysis again. I probably do not have to tell you the importance. Now, this year's, of course, physical science prize laureates are Professor Zhang Tao and Professor Li Yadong for their, boy, I cannot see that, seminal contributions in single atom catalysis, where you use individual atoms as catalysts. I also want to point out that another class of catalysts one often use are nanoparticle catalysts. Now, these nanoparticle catalysts, a salient feature of them is their intrinsic heterogeneity. Now, if you look at a population of nanoparticle catalysts, they always have different sizes, different shapes. One can wonder, what are their catalytic activity differences? Even on a single particle catalyst, it can have many different surface sites. For example, in this bimetallic palladium gold particle, it can have monometallic sites. It can also have bimetallic sites at the interfaces. Can one directly visualize which sites are more active than the others? Furthermore, if you apply these nanoparticles in catalysis, their structure or their morphology often change during a course of a chemical reaction. That will give you time-dependent catalytic activity that is typically not known. Can we visualize or understand these time-dependent catalytic properties at the fundamental level? Now, to study these processes or to answer these fundamental questions, one really needs to study catalysis of individual nanoparticles in real time and spatially resolved. So a number of years ago, my former postdoc, Wei Ling, did an experiment so that he can utilize fluorescence signals of individual molecules to monitor catalysis on individual nanoparticles, which are made of gold. So shown here in this picture that the bright spot is the fluorescence signal of a single reaction product sitting on a single particle catalyst. I will show you a movie here. The flickering is noise. But if you focus your eyesight at the middle, what you see here is flashes. It's like in the dark sky, you have flashing stars. Now, each flash is one catalytic reaction catalyzed by one particle. One can plot out this fluorescence intensity as a function of time, and you will see these so-called off and on telegram signals. Each intensity jump marks a catalytic product formation event, and each intensity drop marks a product desorption from the catalyst surface and a go away in the solution. Now, each off-on and on cycle is a single catalytic turnover. Now, one can even zoom in into this image further and can localize this molecular position with nanometer precision, which is the basis of another Nobel Prize in super-resolved fluorescence microscopy. So what do we have here is now a single reaction resolution and looking at single nanopart catalysis in real time. So one of the first things we learned by looking at the data is that if you look at the catalytic activity for a single gold nanometer particle as a function of time, this activity fluctuates over time, even though every single experimentally controllable condition is kept constant. So what you see here is really the underlying structure dynamics that I alluded to earlier. During catalysis, the surface atoms of the nanoparticle catalyst can rearrange. When the surface structure changes, activity changes. So what you see here is really the functional manifestation of the underlying structure dynamics. Now, since we can resolve every single reaction and also determine its location precisely with nanometer precision, now we can look at, for example, a gold nanoplate catalyst and spatially determine where every single reaction occurs. Now, each dot on this plot is a single reaction. But now we can see reactions happening on corners, along the edges, on top of the facets. One can now directly visualize that the corner has most activity, followed by the edge regions, followed by facet regions. So you have a visualization of a site-specific activity on an individual catalyst. This is done by a former graduate student, Nesha, and also a former postdoc, Xiao Chun. Now, all of these examples that I've given are built on the fact that we're detecting fluorescent signals of a catalytic reaction product. What about chemical reactions that do not have any fluorescent species? Can we do similar imaging down to some similar level? So my former postdoc, Xian Wen, developed a technique, we call it COMPETES, that stands for a little mouthful term here. So the fundamental idea is that if I have a catalyst that can catalyze fluorogenic reactions where the product is fluorescent, I can map this fluorogenic reaction on a single particle with nanometer precision. Now, if I have another reaction, neither the reactant nor the product is fluorescent, but this reaction happens on the same particle surface and where the reactant will compete for the catalyst surface sites. So once you introduce this competing reaction, this original fluorogenic reaction rate will suppressed at all the possible places on the same particle. And that suppression can be mapped at the same nanometer resolution, and that suppression also tells you about this non-fluorescent reaction. So we implement this to look at photocatalysis on bismuth vanadate particles. We can map a fluorogenic reaction on this particle with individual molecule nanometer resolution. He can count the number of molecules at all the possible places. Now we introduce our competing reaction. I'm not telling you what the exact reaction here, but this competing reaction is non-fluorescent. Now you see everywhere this original fluorogenic reaction is suppressed. Then you take a difference of these two images. Turn out in the inverse space, now this image is directly proportional to this adsorption equilibrium constant. of this original non-fluorescent reaction. So what you see here is a visualization of an adsorption affinity of a non-fluorescent reaction, and shown here, adsorbs stronger on this top facet, followed by this lateral facet, and followed by these corner regions. My second story, I want to use similar methods of looking at polymerization reactions. Now, perhaps I don't need to convince anyone synthetic polymers are important in our daily lives. You might have used any one of these things. Now, synthetic polymers are important to make. Of course, they're equally important to study. Now, one of the challenges about the synthetic polymers to study is their, again, heterogeneity. If you have long chain polymers, different chains often have different lengths. If you have copolymers, the monomer arrangements differ from one chain to another. Now, fundamentally, it's really due to the fact when the individual polymers grow in the synthesis process, they grow at different rates, and different monomers are also incorporated unequally. Now, to understand these things, I'm a physical chemist. I thought perhaps we should track single polymer growth in real time, now preferably even at single monomer resolution. So that's what we set out to do. My former postdoc Trimming, student Kerry, another postdoc Suso, developed this technique utilizing magnetic tweezers, where we tether a single polymer between a surface and the magnetic particle. We use an external magnet to attract the particle to stretch the polymer upwards. So now if you have a catalyst here, they can catalyze the insertion of the monomers, the polymer will grow, and this particle will move upwards in Z. So by tracking the position of the particle in Z, we can track the real-time extension increase, which means the real-time polymerization reaction of a single chain. Now, the underlying chemistry, again, is another Nobel Prize chemistry that is called ring opening metathesis polymerization. We have a ruthenium catalyst here. The other end is linked to the surface. Catalyst is immobilized on the magnetic particle. We flow in the cyclic olefin, coordinates ruthenium, form a ring opens, and the monomer inserted. You repeat the cycle, the polymer grows. Now, to track this particle in Z, we shine light from the top. We collection transmission images from the bottom. Optical microscopy can have these diffraction patterns when this particle is away from the focal plane. Now, when the particle is closer to the focal plane, it forms different diffraction patterns. So by analyzing the pattern, we immediately know the Z position. Now, I'll show you a movie. If the movie plays, the movie is not playing. Can someone click that picture again? Let me try it again. Okay, I can't do anything. So imagine in that movie, you have a particle, you have a polymer grows towards you, and then the ring pattern will just grow bigger and bigger. Is it really playing now or not? Confusing now? All right. By analyzing this movie, we can look at how a polymer extension increases as a function time. What we discovered unexpectedly now is that the polymer extension does not grow continuously, but have these long wait periods followed by instantaneous jumps that comes from this formation of this non-equilibrium entanglements that form probabilistically and then unravel also probabilistically, and turn out these non-equilibrium conformational entanglements was never known before and also controls the polymerization kinetics. So this magnetic tweezer technique was great for us to follow individual polymer in real time, but did have one limitation, that we could not resolve every single monomer being added in. We thought maybe we can come back to fluorescence microscopy. So my former postdoc Xiang Chen, Rocky, and Xuanwen developed another technique. We call it CREATES, that stands for this particular term. What we have here, again, is a surface grafted polymerization reaction where the polymer can grow by adding monomers. But this polymerization reaction initially carries no fluorescent signal. But now we have another reaction that happens on the monomer that is tagged with a caged fluorophore. Now, since the monomer of the fluorophore is caged, it does not have fluorescence, so it can be supplied with high concentration, so the polymerization reaction can continue or go on. But now we can zip of the laser light, time it in a proper way. Once the monomer is added in the polymer, we uncage the monomer, release the fluorescence. By detecting the fluorescent signal, we can see every single monomer to come in. So by coupling two different reactions, we should be able to monitor every single monomer being added into a growing polymer chain. So we immobilize the catalyst on a silica particle. That the catalyst is also fluorophore labeled. So here is the scanning electron microscopy of the Maka particle. We do fluorescence imaging, and we can localize the catalyst is here in this dark image. We can supply now our caged fluorophore monomer A that carries a green color and do our uncaging fluorescence detection. Now I can see every single monomer being coming in a sequence as a function of time. Now for every single monomer we detect, we can also localize its position, and now you can see every single monomer is landed on a single catalyst. So what we have here now is a single polymer growth with single monomer resolution. Now we can use two different types of monomers, A and B, that carries green color or yellow color. By visualizing every single A, every single B being incorporated onto a single catalyst, the landing on top of each other, now we can plot out the A and B as a function of time. So now you can see B monomer, A, B. So not only we can see every monomer coming in, we can also determine the exact microscopic sequence of a synthetic copolymer. Of course, this is just one. We can look at many synthetic copolymers. We can microscopically determine the exact sequence of a single polymer chain. And turn out these sequences shows a blocky pattern. This is supposed to be blocky, not blacky. Now, we think now this is a step towards ultimately, maybe we can do sequence function correlations to study synthetic copolymers. Now, in the remaining minutes, I will show you a topic that goes into biology, looking at bacterial proteins inside a cell. Now, a bacteria is a little unfortunate compared to us. They often live in very, very harsh environments. They could be surrounded by heavy metals, antibiotics, or detergents. All of these molecules can be toxic and kill the bacteria. Bacteria, of course, is also smart. It has developed many mechanisms to defend against such toxic chemicals. One of the most general mechanisms is using efflux, using protein complexes that have an inner membrane pump, outer membrane protein pore, and also periplasmic adapter protein that can pump the toxic chemical, for example, copper or silver, out of cell so that this cell can survive. Now, if you look at these structures at the cartoon level, these complexes link the inner membrane and outer membrane through the cell wall together, potentially form very rigid linkages that make this cell envelope or the periplasmic space more rigid. And that potentially can risk this periplasmic plasticity that was known to be important for a gram-negative bacteria such as E. coli that I've shown here. Now, people always wondered, maybe such multi-component complexes do not have to be assembled all the time. They can undergo dynamic disassembly into its pieces and only form the assembly when they are needed to pump out toxic metals like that. So my former postdoc Tae-Yan and student Ace, decided to take a look at this, what is true inside a living cell. So the strategy is very simple. If we can tag this inner membrane protein with a fluorescent probe and image and track its motion inside the cell, this should be a stationary object because linking the cell envelope, and this would be a much more mobile object moving around along the membrane. Indeed the case, we can track these individual proteins in the cell, for example, shown here, by taking snapshots of images. We can track its motions. We can overlay many of these motions together. Now you can see sort of slow stationary objects. You can also see very fast moving ones that corresponding to the mobile or the stationary objects. One can also determine that in the absence of this toxic chemical, these two states exist in 50-50% ratio. But now if you put this toxic chemical in the surrounding and this equilibrium shift to the right, so you can assemble these protein complexes to pump the metal out of the cell. It was great for us to watch how these proteins behave inside the cell and learn about the properties. We thought, can we actually do something to the cell and manipulate this protein complex? So the idea was, perhaps we can put this individual E. coli cells into a taped fluidic channel. One end is bigger than the other. By squeezing this bacteria into this channel, we can deform it. Now, if these complexes make linkages on the cell envelope, by deforming the cell, we might be able to disrupt the assembly and compromise its function. You may wonder, why should one do this type of a squeezing into a tight space in the first place? Now, it turned out, in nature, for example, in bone tissues, bacterial cells can squeeze into these tight spaces to escape from macrophages. Bacteria can also live in aquatic environment that is surrounded by hydrostatic compression. If they adhere to the surface, they also have adhesion forces. If you have a solution flow, you also have shear forces. So these mechanical forces happening in nature actually can also be applied or present in this device, but now in a way that we can control it precisely. So we collaborated with a mechanical engineer, my former colleague Chris Hernandez, and her student Melanie, and also my former student Lauren, to look at this. My collaborators made these devices. They have microfluidic channels. One end is bigger than the other. Now individual bacteria can be squeezed in. Now Lauren can come in to do single molecule microscopy and tracking the motions of every single protein inside a single cell. Indeed, we can show by increasing the solution pressure difference between the upstream and downstream with increasing delta P, we can indeed disrupt the complex of this assembly and make them into pieces and then compromises the bacteria's defense against toxic chemicals. So hopefully, I have given you 3 examples that give you a little flavor how one can use fundamental microscopy to learning about fundamental chemical processes in a variety of different topics. I want to thank you for your attention. I also want to thank my former group members and also the current group that did all the work. Thank you.
So thank you very much. Very enlightening talk about single molecule chemistry and how one can really follow the individual molecules and all the reaction and processes. So the next and the final keynote speaker this morning is Professor Jinyao Tang, and he's a professor at the University of Hong Kong, and he will tell us about active phase transition and new material on move. So, Jinyao, please.
Okay. Thank you very much. It's my great pleasure and honor to be here to share some of my work. And firstly, it's congratulations to Professor Zhang Tao and Professor Li Yadong for their works on catalysis. So I will be your doorkeepers to prevent you from the lunch. Sorry for that. But hopefully for the next 20 minutes or so, I would like to introduce you a new field, which I borrowed the word from Richard Feynman. It's a field that little has been done, but in principle, enormous can be done. So that is a new area, that is a new material on move. Yeah, so if we actually looking around us, so if you're having a good eyes, so you're seeing these kind of behaviors, right? You see shattering of the glass and diffusions, rotting and rustering. And so we call it these as the arrow of time, so the entropies. So things is actually changing from an order state to more or less disorder state. So that is the nature of our universe. So on the other hand, if we are thinking more carefully about this, so this is actually nature of the more or less dead world, so whenever it's not really living. So if you're looking more on the other side, which is livings, like bacteria or something, right? So these things are different. So they actually starting from a very disorder state to a more or less order state, for example, this kind of a self-assemblies from the very beginnings. So what looks like there is some kind of gap between the life and death. So there must be some kind of missing part in between of this. So what kind of missing part is there can bridge these two areas, because after all, we're living in the same world governed by the physics. So one thing actually very easy to think about is motion, right? So at the very beginnings of science, people are thinking like something that moves, that is life. Something that is stationary, stay there, so that is dead things. Right? For example, these kind of moving bacteria, so this is swimming around, you can see them very easily. On the other side, if you're having tiny particles, you see they actually also moves, but it also moves in a very different ways. So these ways, Albert Einstein told us, because they're actually bounced by the nearby molecules or gases in the solutions. So they're constantly jiggling around. So you can very quickly distinguish this kind of motions versus this kind of motions. They are different, okay, without doing any mathematics. But is there any way we can bridge this one, finding a gap between that or bridge between that? So this is a little bit about 20 years ago, people start to find some kind of inorganic particles. So this inorganic particle, very simple. It's gold and the platinum particles. And you stick them together, and you're putting inside the hydrogen peroxide solutions, which we actually use it to disinfectants. So you put there, I can see these particles start to swim. Obviously, they're just like this, but this has nothing to do with the living things. They're not life. So it looks like there is a missing parts we find bridging the life and death already. So for the, my lab, for the last, a few years, we actually working on this field. It's, we call it a swimming colloid or active colloid. It's essentially, it's a catalyst. But instead of doing the catalyst really doing good things, like has a product, we're having the catalytic interactions or reactions on it. For example, like we're shooting light particularly. We were shooting light onto our particles. They're starting doing some kind of surface chemistry. When they actually do, this surface chemistry will propel these particles start to swim, right? So different kind of swimming. There could be phototactic, and that means the drives or chasing the light, or they could be photochemically, or they're just chasing different kind of colors, or different kind of polarizations, or different kind of phase of the material of the light. Either ways, these are our new material on move. But like when people are asking, like, what you guys are doing here, like we're trying to say is we're trying to build some nano robot. Eventually, we're going to use it for like kill cancers or something like that. But today I'm going to say something else. Is maybe we're actually using this as a new building blocks, fundamentally, for materials. Because if you're thinking about new materials, like what kind of materials you're like sitting on, you're facing on, it's just made by atoms, whatever the atom it is, right? So this, no matter how sophisticated it is, it's an aggregate. It's just a bunch of the atoms stick together, so maybe some kind of molecules. And they arranged in a different ways, could be the crystals or amorphous or gels. But in either ways, these materials is dead, right? So they're not doing any kind of non-equilibrium things. They're actually sitting at the bottom of the energies. However, if you're looking differently, so crossing these boundaries, like if we have some kind of colloids, some kind of particles, they start to move, they could self-assemble into some kind of intrinsic, complicated structures. But we never think this as a material. We're never using them in that ways. But like in nature, there are many of them. So for example, there's motor proteins, there are bacteria, there are cells, like the birds, also yourself. It's a active things, but it's not a material. Or maybe like it could be a material, right? But either ways, once we cross these boundaries, we're starting from the equilibrium system to non-equilibrium systems, we can build something different. If you have a static parts, right, so like here, so we're going to have the static assemblies. Well, we can build them using the very classical thermodynamics. But if you introduce something else, like the moving parts, something can start to move, maybe we can build something more sophisticated, right? So something more intrinsically different. From a thermodynamic point of view, like assemblies, we, as our materials, is actually over here, right? So we are actually equilibrium at the energy landscape. It's somewhere here or somewhere here. So either global minimum or locally minimum. So I call it equilibrium materials, whatever, the wood or something dead. So if you are clever enough doing some chemistry on that, for example, we can have some kind of transition from one equilibrium state to another equilibrium state. For example, like Professor Vivian Yan's group, they're actually developing this kind of photochromic material. So you're shooting light on it, so it's switching from one to another. So, but either way, so they're actually sitting on the bottom of the energy landscape. So we call it responsive materials or functional materials. But if you look closer, like there's large areas, like in the energy landscape, we don't know what their property is because they are transient, they're not stable, so you cannot access to it. But however, if we actually having some kind of dissipation reactions, some kind of interaction on it, maybe we can stabilize these active species, so make them into a useful material. So that is actually like my goals of comparing like the traditional materials versus active. Just give you examples, very simple examples, like when we're actually learning basic chemistries, like it's like this. So if you're having two kind of particles, like for example A and B, it could be molecules, it could be anything. right? So there is two things could happen. One, these two things mix, so we call it immiscibles. Another thing is it could be just oil and water, so they could be immiscible. They separate each other. So why this is the case? Because if you have A and B, they are very like each other, so their interaction is equal to each other's. So entropy is going to drop in, so you're starting getting these mixtures. However, if you have the particles A wants to stick with another particle A instead of B, so they're going to be phase separated. So they're basically separated from each other's, becomes immiscibles. So by interaction difference, so you're driving these separations. Chemistry-wise, like we actually could do this in the experiment. So we're actually inspired by the dye-sensitized solar cells invented by Michael Gressels. So this is a solar cell. So this is what solar cell really does. You have the titanium electrodes, and you have some platinum electrodes. So in between, there is some photo redox shuttles and some dyes. When the light is shooting on it, so electron is transferred through this channels from the electrode to the dyes, to the redox shuttles, to the titanium, and then go to the external circuit. So that is dye-sensitized solar cells. For us, we don't have that. We just have particles, and we load the dye onto the particles. So that means there is no electrode, there is no external circuit, so there is no energy, I'm sorry. So we wasted the energies, but there is still catalytically doing the reaction. So this chemical reactions is, so the electron goes through here, but they basically waste it. So we're wasting a lot of energies, but also we can generate some chemical reactions on the surface. This chemical reaction on the surface is going to generate a chemical potential difference, or the chemical gradient on the surface. We said the electrode is polarized. So thinking about if you're having particles nearby, because this is a concentration difference, so they're going to face this kind of concentration difference and generate some kind of Faradic flow. So in this case, it could be repel or attraction. So in this particular case, they could attract each other. So essentially, we could have particles, and you can excite it with light. So transform the passive particles into active particles. Fortunately, we can actually do this in a more spectrum selective way. So you can use different colors to do that. So you can actually getting the passive to active, or passive to active to active interactions. Some is stronger, some is weaker. So we're actually doing the experiment, actually measuring these interactions. So for example, if you have a red particles, so red particle means they actually absorb the blue light. So when they do, so the interactions between these two particles getting stronger and stronger with the intensity of the light getting stronger, while the blue particle doesn't absorb the blue, so it doesn't do that, versus the blue particle absorbs the red, so something like that. So again, kicking the physical chemistries. So if you're thinking about the mixtures to the separations, so this is called the phase transitions. For example, you have the well-mixed system, and you could think about this phase diagrams. If you cool it down or heat it up, you are transferring from the one phase to another phase. So you actually could get this phase separations. But that is by changing the temperatures. So in our case, we're actually having a chemical reactions, because over here you can have this temperature over here, and this is a difference between the interaction, right? So which can be controlled by the light. So if this numbers is going greater than 2, so they're going to phase separate. So we can do that, okay? We have the interactions. So this is the axis is light intensities. Across these boundaries, you're starting to get this phase separations. So again, we can use a blue light to excite the red particles, or using red light to excite the blue particles. So essentially, over here, you can see this phase separations from the blue light gradually increases, goes degraded to the red light. So they're phase separated. They're both phase separated, but the phase separation is different. In this case, the red particle is inside, versus here is blue particle is inside. If you're doing this a little bit more, so for example, you can have this primary color, so the red, the blue, and yellow. So you can have this phase separations in a more color-sensitive ways. So you shooting light on it, and you move the boundaries into the phase separation regions. So by shooting different colors of the light, so you're starting to get different kind of phase separations, right? So color-sensitive ways. So a little bit more. So if you put in more of these particles, they cannot do that easily, but like they're going to like phase separate it in a little bit more like this ways. So you're shooting light on it with a pattern on it, because as a primary color, you put them together, it's a black. But when you're actually shooting light, they phase separate it, they're showing colors already, right? So just like one thing is coming out. So if you're shooting the red on it, so they're showing red. If you're shooting the green, they're showing green. So you can put in a different kind of patterns on it. Obviously, that's going to follow whatever the patterns you get it. So this is actually the same ways of the squid actually changing colors to the environment. So when these squid actually face, okay, whatever the environment color is, so they're going to try to push their pigment on the surface, so that is going to change the appearance of that. And remember, this phase separations is dynamic, so there's not thermodynamic equilibrium, so that means it's transient. You can actually change in them into whatever these patterns could be, right? So you can change from one to another and to another, continue going, right? So this is truly dynamic in the sense. Right, so this is one thing, like, because like when we're actually having these particles, they're pretty much random, they're chaotic, they're not really forming some kind of order structures, so we call it the liquid or colloidal liquid. So we can do it in the solid state as well. So like, for example, they form some kind of more closed packed one. So in the particles in the world, like we can have this one. So this is silica particles, they actually forms close packed regions, like assemblies. This is opal. Like from a jewelry point of view, this is interesting, but from a scientific point of view, it's not very interesting because this is only thing they actually forms. But if you look at the atoms in chemistries, so that could be different because chemistries, we know the atoms have a different kind of orbitals, electrons. So electrons could be spherically symmetrical, could be not spherically symmetrical, right? So because they are not spherically symmetrical, you could have all kind of crystal systems, which is more varieties, right? So there can be more functions to that. Can we actually build our active colloids in their more asymmetrical ways? So actually very simple as well. So if we have particles like this, similarly, previously we're actually shooting, let's say for the red particles, we're shooting blue light on it, but this time we're actually shooting red light on it over here. So the red light shooting on it, it's not going to absorb very strong, so that's going to pass through, but because of the reflective index, it's going to focus on a tiny spot on the particles, but it's going to do a little bit of excitation, so there's still some photochemical reactions, catalytic reaction on it. So for example, it's going to be having a reaction over here, and this particle becomes like asymmetrical particle. So if you're just shooting like that, so this particle starts to move. But if you're shooting light from the both directions, it's going to be more like a p orbitals already, right? And we can see that, okay, we're shooting light on the both sides, so you can see this, okay, a little bit attractions and repulsions, but this really looks like a p orbitals. So we can try to massage this p orbitals, whatever the shape we want to. So you can imagine if you have many of these particles around, and you're shooting light on it, on both sides, so they're going to arrange in a certain ways, right? So this is actually what we see. Very simple. You have like a lot of particles and shooting light on it, and they're actually arranged into this linear shape of that. So this is a little bit more like a p orbitals. And the good thing about this is, because this is just like shooting light on it, so we can have s, p, and d, f orbitals. So if you're shooting light from whatever the direction you want, so you could have all kind of interactions as you want. Some of them is like the ps orbitals. Sometimes it's not really have the symmetries available for example, over here, so this is not whatever it is, right? So like it's not a p orbitals anymore. But either ways, we can have these kind of interactions on it, and these interactions is going to lead to a kind of assemblies. So predictably, you can just like using a very simple statistical thermodynamics, you know it's going to assemble in these different structures. Because in two-dimensional space, there are actually 5 possible lattices, could be possible arranged. In our ways, it's going to be like these 5. So you're shooting light on it, and they're forming all these 5 lattices, possibly, on the 2D space. Right? So what we can do about this, so like at this moment, they're not doing much, right? So we have this dynamic particles, assembly crystals, and these dynamic crystals, you can shooting light, let's say a laser on it, so it's going to diffract the laser's beam. So, but because it's a dynamic crystal or active crystal, so you can use it, one light, or basically a light around it, to control another beam of light. So it's just like a circuit, right? So like in the transistors, you have the electricities to control another electricities. So we can use it to control the light from another light. Right? So it's not very quick because the particle-wise, it's relatively big. But like on like every second, you can switch it a few times, something like that. Right? So that is the active crystals. And because we actually could make this p orbitals, d orbitals, whatever the orbital is, and massage like it's changing the shape of the orbitals, so you can actually getting a little bit about the colloidal chemistries on that, right? So they can form this kind of polymers, so there's kind of 2 particles around, and you can have this crystal lattices and the forms just by changing the light intensities, light frequencies, and light directions. So without like much, I think it's that's pretty much I want to talk about. But our idea is, so switching from the building blocks, which is very like simple thermodynamically equilibrium building blocks, to active building blocks, we may be able to access some active clusters and phases, which is not available, maybe some properties that could be possible for us. And for example, which I don't have time to actually mention, is some of the properties, assemblies, that is not possible for thermodynamic equilibrium system, for example, this swarming systems, or intelligence system, for example, yourself, self-polarizations, and we also could make it into the molecular scales. Hopefully next time I can share you about this. So making these all dynamic assemblies in real materials. Without too much, like I think it's, we expanded from the equilibrium material systems to a more and more active systems. And I think it's, we're starting with like very finite known to like infinite unknown systems. Okay, so that is all. I want to make thank you to my groups and the funding support, and also thank you very much for your time and attention.
Thank you so much, Professor. Please stay with us. Could you please come forward, because we are going to have another session. We'll have your participation as well. And our experts just explored topics such as the acid catalyst, single molecule chemistry, and active phase transition, highlighting the potential of chemistry to address global challenges and inspire future scientific advancement. And we are very happy to have a panel discussion coming up next. For the panel discussion, we'll delve into the role of chemistry as a central science that connects various disciplines, driving innovation, advancing interdisciplinary research. We are very honored to introduce our moderator, Professor Vivian Wing-Hua Yam. And our panelists, including Professor Chen Peng. Professor Chen, please. Professor Cui Yi. Professor Benjamin List. And of course, on the stage already, Professor Tang Jingyao. So I may pass the time to our moderator. Thank you.
So thank you very much. So I would like to thank all the speakers for all the wonderful and fantastic talk, giving us a flavor of how chemistry will be able to play a key role in changing our world and contributing to a lot of global challenges. So today we'll have a discussion. So thank you for also coming for this panel discussion. Today we'll talk about, because the title of this section is really chemistry is a central science, and I guess all chemists would agree to that. So maybe can you share with us, maybe Ben first, on how you think of chemistry in really, do you think it's really a central science? And how would it contribute towards really meeting all the global challenges? You already show us catalysis is really one of the very important things that changed the world, and so please.
So, well, I like to start by sharing with you how I got interested in chemistry, because it was a deep misunderstanding. I was 11 years old, and I kind of knew already the world is made up of atoms and molecules and matter and so on. And so I had the impression that chemists understand everything, literally the whole universe. And so I was drawn to this because I had these philosophical questions on my mind. So how, why are we here? Where are we going? And so on. And why is there something and not nothing? And then when I became a chemist, I more and more realized, unfortunately, these questions will not be provided, or the answers to these questions will not be provided by chemistry. But I was already hooked, and chemistry is the central science, as you said. It's like so incredibly relevant for our life. I think that's really unsurpassed by any other human cultural activity that we have developed over the last few thousand years or so. And while I'm like a fundamental researcher, I like fundamental science, and I'm happy that I share this interest with you here in Hong Kong and in China as a whole. Other countries are moving more to applied science. During the pandemic, actually, I realized how impactful it is if we look at actually real problems like batteries or something like that. Like how can we contribute to our life on this planet? And I'm very enthusiastic now about using our research in fundamental science and to solve actual real life problems.
Yeah, thank you. So Yi, how would you sort of give us a flavor?
Can you hear me? Sounds good. I think, just to remind everybody, even though I'm in material science department, I have my undergraduate degree, PhD degree, and postdoc all in chemistry. So I'm fundamentally a chemist. Maybe one way to think about resonate what Ben just said. When you look at chemistry, it's the foundation. Chemistry can be so important for energy, so important for life, important for huge amount of industry areas. So it's really foundational. Fundamentally, chemistry really offers first the tool to make things, produce things. If you cannot produce things, you just cannot study that. You cannot use it. So that's so important. And making things, synthesizing things. And also chemistry is dealing with complex systems oftentimes. The real life is fundamentally complicated. And chemistry is dealing with that. I mean, this is common, it's probably refer back to physics. Physics want to study simple system. And chemistry is dealing with a lot more complex systems. It's just no surprise chemistry is a central science to everything we do.
Yeah, thank you. Yeah, chemistry really connects between biology, right, physics, engineering, and everything sort of like you can think of. And so, Peng, can you say something on that?
So I consider, I guess, chemistry as a central science as sort of how it interfaces with other disciplines, perhaps in two directions. So I say one direction, chemistry have benefited from the advances of other disciplines. In my own research, microscopy, which is mainly perhaps advanced in the physics field, they have provided tools that we can now looking at fundamental chemical processes at a deeper level. Now, electron microscopy, synchrotrons are all techniques coming from, let's say, mainly other disciplines. Now, the other direction is chemistry, of course, provides a lot of solutions to other disciplines, perhaps understandings. Now, biology is very complex. At the bottom of the biology is actually chemical processes make biology fantastically complex. And I think understanding the chemical processes provides insights into biology, and I think this is another feature of chemistry being a central science discipline.
Yeah, thank you. So particularly your work looking at single molecule, right? Because what we see usually is a whole ensemble of molecules. It's really a time average thing, even the kinetics, right? But you're looking at individual ones that will be behaving quite differently. So it's interesting in a way. So Jin Yao?
Oh, thank you. Yeah, I just want to ask others in the audience to think about what chemist really is. So chemist is really coming from the alchemist, right? So alchemist. So what do you think about the alchemist or actually other field? So if we are actually thinking about the physicists, they're actually doing equations, those kind of things. As mathematicians, they're going to do very sophisticated things. And chemist is a doer, right? So it's actually doing, our hands get dirty, and we're actually getting things materialized. And the other side is because chemistry is really make things works. So this is also why I think at this moment, a lot of this other area people actually get in and getting Nobel Prize for chemistries with physicists, with mathematicians at this moment. But it's in one way where we're actually thinking as a chemist is it's sad other people comes in, and other ways actually this is a good area everybody wants to get in. Thank you.
Yeah, thank you. So actually there's no sharp demarcation these days, right? So everyone is trying to have all these different tools just to really target very important, large, significant scientific problems, meeting global challenges and so on. So one should not sort of just say, I am a chemist and I will always be just learning chemistry. So we have to learn many different things, peripheral, and learn the jargons to talk to people, to have all these interdisciplinary collaboration. So Ben, you mentioned about very fundamental importance about catalysis, right? And photosynthesis, which is also related to that, it's really the bread and butter and fundamental of the origin of life, right? So how would you see chemistry can contribute even more, or which are the areas you think are so important that we'll be able to make more significant contributions in meeting global challenges?
I think the origin of life is a great topic that you raise. In my society, in the Max Planck Society, right now, this area, the origin of life, is dominated by physicists, astrophysicists, and biologists, which is kind of weird, right? Because, as you point out, this is fundamentally a chemistry, by definition, a chemistry question, right? Before it became biology. So I think that's a great area to work on. But for me, actually, right now, what I'm deeply fascinated with, and I mentioned this in my talk, is the CO2 conversion. Taking the CO2 back from the atmosphere and converting it into something that you can store and you can make energy and all sorts of beautiful things with. I think it's just sort of a grand challenge, and it's so beautiful for us chemists to also contribute to this problem.
So Yi, you talk about earth abundant elements. That's very important as well, right? So and also beyond lithium battery and of course other things. So can you share with us some of your thinkings about how we could contribute more in solving global challenges?
Absolutely. So I want to share maybe just slightly broader of, in chemistry, you look at the past few hundred years has been foundational to build to the building of modern civilization. But looking at the grand challenges right now, climate change, sustainability as an issue, chemistry will be able to contribute to nearly all of the important areas. So let's list that. storing energy, I just talked about today, enabling complete sustainable mobility and stationary storage, decarbonize the whole electricity grid, right? That's a very important one. And also looking at decarbonizing, let's say remove CO2 from the air, maybe ban your idea CO2 decomposition, carbon and oxygen. Fantastic. How do you capture CO2 and utilize that? And also natural gas, the methane leakage, right? It's 1.7 ppm concentration. How do we deal with that? This need to rely on chemistry. And then how do you generate clean steel? New type of cement, maybe it's a new chemistry to enable that, right? Low carbon cement, low carbon steel. And then how do you enable hydrogen economy? And how do you do material circularity and new type of agriculture as well, sustainable food generation, instead of utilizing this very CO2, greenhouse gas intense process? This chemistry certainly coupled with biology for sustainable food and agriculture as well. So nearly everything we look into, you got to involve chemistry.
Yeah, thank you. So Peng?
So I guess grand challenges in chemistry, there are many of them, right? And energy technology making batteries. Now, from my point of view, is that I have been studying sort of chemical processes. And actually, one of the grand challenge processes that I want to study is batteries. And these are solid-state reactions. Can
we can collaborate now.
Perhaps. I don't have a good idea yet. How can visualize battery reactions?
We will have lunch together. We'll talk about collaboration.
We can talk about that. Okay, talk about that. Now, that Vivian mentioned, as chemists, actually, when we think about chemical process, we always think about individual molecules, right? When we think about organic synthesis, we think about A reacting with B to C. That's what we think. But we never measure that way. Okay, we typically measure a million A's reacting a million B's, generate a million C's, right? Of course, modern techniques now can allow you to look at individual reactions, but not all of them. Experiments that I talk about are essentially selected examples that I could do it. There are many examples I wanted to do, for example, battery reactions. I don't know how to do that yet. And active materials, can we visualize these things even down to a more molecular level? That would be fantastic.
I'm doing it.
All right, great.
Okay, so Jinyo?
Oh yes. So actually, from my point of view, the global challenges, there could be many, but at this moment, one very hot topic besides the energies and the precautionary energies, there are actually people are starting to work on the complex systems, where the system is out of equilibrium from the AIs, from the air systems, from whatever the live societies. And a lot of these is actually an unexplored area, and for computing as well. There are many things, but from scientific point of views, we as a scientist or whole society, human beings, is trying to work with a thermodynamic system for hundreds of years. But for the non-equilibrium systems, maybe it's just started. And there are applications there, as I said, there could be AI computings, and it could be possible to build artificial life. And this artificial life is arguably a computing machine. And maybe that is more or less a different ways of thinking what new materials and new application could be. And it could be a little bit far away, but I think it's looking further in the futures that could be.
Yeah, so you also mentioned about some of your micro swimmers, active, colloids and all that. And then they can sort of phase segregate to have the frog skin sort of camouflage and all that. But then you also mentioned a little bit about going to cancer cells or, nanorobots. So because we have been talking quite a lot on energy and catalysis sustainability, what about chemistry in terms of contributing to health? Biology, of course, photosynthesis is one. Yeah. So can you enlighten us on that?
I mean, this is something I try to also mention in my talk. What people who are not chemists forget is that that chemistry actually contributes to our health more than anything else, right? It's not, I mean, nothing against the doctors, they heal us, it's true, but they're not the ones who design and make pharmaceuticals, for example. And one vision I'd like to share with you, I think this is also would be a grand challenge if you start your own career now and you think about what to work on. I would suggest to take a look at bioorthogonal catalysis, right? Bioorthogonal chemistry we know, but can we come up with a catalytic reaction that works orthogonally to the chemistry that is ongoing in our bodies, and then have a catalytic drug? You take a little bit of a pill, like, I don't know, 1 milligram or something, and that heals some disease that you might have in a catalytic sense. I think that would be something really incredibly useful. So, now, just a little suggestion for you guys.
Yeah, very exciting. So just like what you have a PPB level, and then you'll exactly. Kill yourself. Yeah, okay. So, Yi?
Well, I think what Ben just said remind my colleagues' work, our Nobel Prize winner, Karen Bertozzi, and that would be really cool. So another area, perhaps, if related to life science, is actually brain. How does brain work? How does the whole body, how do you form recognition and so on? I think this is very rich. It's just not only just biology, it's a lot of chemistry. And there can play a very important role in terms of designing the tools, understanding the molecular level mechanisms, understanding the interconnectivity of different molecular pathways can enable this. This is super exciting. Yeah, I don't work on that anymore. So, but I just for about 10 years I worked with my colleagues, Professor Bin-Xiao Cui at Stanford on this. But running out of energy to work on so many things, better concentrate on energy.
But you're amazing. I remember you were trained as an inorganic chemist, and now you are doing all these materials, fantastic materials.
That was why actually Li Yadong was my chemistry professor at USTC in organic chemistry. Yeah.
Okay. Yeah, sure. And Pang?
So maybe one particular area that I should mention is antibiotic resistance. And this is probably one of the biggest issues in health. I don't want to say that I know much, but one of the motivations that we studied looking at bacteria of the efflux pumps was sort of motivated by that, because one of the well-known antibiotic resistance mechanism is the efflux. Okay, bacteria is so powerful of pumping every toxic chemical out, and the drugs just do not have effect. And that gave us opportunity to look at proteins, how these proteins inside the cell. I cannot say, I'm not sure whether I will be able to say that we ever provided any solution to antibiotic resistance, but looking at these fundamental chemical processes of how these proteins work together has been a very rewarding experience. And I think maybe for other younger researchers looking into these type of issues will be exciting as well. Okay.
Yeah, but it's really interesting. You have this sequence specific. You were able to work out the sequence of all these copolymers and so on. It's really amazing. Yeah. So Jinyao, can you share with us?
Oh, yes. So I think it's for health, obviously we're working with something very different with other, like we ordinarily work on. Like ordinarily we like ourselves, like life is a complex system again. It's thermodynamically not equilibrium, like far from equilibrium actually. And nowadays people are working with the drugs or a lot of the case that it could be bindings onto certain targets, but later on they actually failed. So I think this is a shortfall for current research where we think this life can be like just like piece by piece together instead of a holistic view of what life is. And they are far from equilibrium. There could be amplifications. Those kind of works requires different kind of mathematic calculations or method, and also different kind of statistics calculations, or as well as a theories, and maybe like as active matter chemists, actually, like we think we're making insight into the area. Of course, another thing, as you can already see, a lot of the researchers in my area is trying to make the drug delivery things. I think it's a little bit far or a little bit too rushed, but it could be the futures.
So thank you very much. So time is up. So thank you very much for all the very insightful advices to our young people. And it has been a wonderful time having you here in the panel. And can we give a round of applause for all our speakers?
Thank you so much for insightful sharing. Could you please rise and then we can have a photo together? Let's have a photo together. And then, okay, our official photographer is ready. Just have a look to the center, please. Maybe we can have the photo first, if you don't mind. Yes, please. Thank you. Okay, please continue to have a look to the center. One, two, three. 1, 2, 3. 1, 2, 3. Okay, one more to go. One more to go. 我们再来一张。1, 2, 3. 1, 2, 3. Okay. Thank you. Thank you so much. Thank you very much for the insightful sharing. Thanks a lot. Wow, I think this is a really special and very interactive sharing that we understand more about the topic. Thank you so much, everyone. This is the finale of this section. We are about to have lunch. For those who have registered for the lunch, you can just follow the instructions from our helpers to the venue. And then don't forget that we will resume the summit again at 1:30. So we are going to have an amazing keynote speech coming up. So see you at 1:30. Thank you.